Thank you so much for the kind introduction and also for the invitation to be here. So it's really a pleasure to get to interact with you all and share some of the work we're doing in machine learning for scientific discovery. My field of interest is primarily in fluid mechanics. So a lot of the examples I'm going to give are in fluids, but really this is much more general for any complex system that's multi-scale, nonlinear in space or time. Now, before I start, I want to acknowledge my many excellent colleagues, collaborators, and co-authors on some of the work I'm going to show you. And I especially want to thank the postdocs and graduate students in the middle row who really did, the majority of the work I'm going to tell you about. So I like to think about the interface of machine learning, modern methods, with classical challenge problems in dynamical systems and control and in scientific discovery. And so I'm going to oversimplify machine learning. I'm going to say that this is essentially just building models from data using optimization and regression. Now, this is a bit of an oversimplification, but this essentially points out that these new techniques in machine learning fit in nicely to efforts we've been working on for decades, if not centuries. And so the dynamical systems tasks in blue that I care about are things like reducing the dimension of very high dimensional systems like fluid flows or brain dynamics, modeling how these coherent patterns evolve in time, optimally sensing and estimating and controlling these complex systems. And in all of these cases, the challenges that I have in blue end up manifesting as very challenging optimization problems in pink. So my optimization problems are difficult because the physics of my system is nonlinear, because the physics is multi-scale in space and time. And this leads to very high dimensional, non-convex optimization problems typically. And what I want to point out here is that those are exactly the kinds of problems that modern machine learning is getting very good at. So if you think about training a deep neural network, this is a high-dimensional, non-convex optimization problem. And so some of these techniques also directly apply to our classically challenging problems of modeling, prediction, and control in dynamical systems. Now, we believe that this is possible fundamentally because patterns exist in your data. So this is why we believe that we can model fluid flows and neuroscience and climate, is because there are patterns, even in very complex data and very complex systems, patterns exist. And this is the same principle that allows us to work on machine learning. Machine learning is all about extracting meaning from the patterns that exist in your data. And so before talking about some of the specific examples, I want to give you a little bit of an overview of what we do in my lab. So in my lab, I love dynamical systems. Everything I care about in the world really lives up in this blue box of dynamical systems, whether it's a fluid flow, a neuroscience system, your brain, an epidemiological system, how a disease spreads on a continent. These are all high-dimensional, nonlinear, multi-scale dynamical systems that vary in space and time. And we want to be able to model, predict, and control those systems. So a really big part of my group works on building models directly from machine learning of these dynamical systems, models that are interpretable and generalizable. We also spend a lot of time directly designing control laws for these systems through trial and error. Maybe some of these systems are too difficult to model in an interpretable way, but maybe I can learn a control law in a kind of how biological systems do, through trial and error, through experience. Things like reinforcement learning control. And then the third major part of my lab is in designing optimal sensors and actuators to manipulate these systems. And this is very much biologically inspired. So for example, flying insects, all of them have strain-sensitive neurons distributed across their wings. And they use this information, these neurons give them information about what their wing is doing, how they're, what kinds of fluid they're interacting with. And so we would like to understand how to place sensors in our engineering systems for advanced estimation, prediction, and control. Okay, good. So I'm going to start telling you about how we're using machine learning to discover models for complex systems. And I'm going to start off with this example of a turbulent fluid flow with Jared Callahan. So there's a notion in classical physics called dominant balance. And what dominant balance says is that if you have some complex equation governing a physical system, some partial differential equation with lots of terms, in some regions of space and time, you might locally only have a subset of the physics active and balancing each other, that are dominant and balancing, and the other terms in the physics might be approximately zero. So we're going to see if we can design a machine learning algorithm to automatically uncover these dominant balance regimes. This fluid flow past a turbulent boundary layer is from the open source Johns Hopkins Turbulent Database. And so you can download this and try this out yourself if you like. So when we deal with a flow like this, the first thing we do is often compute these Reynolds average Navier-Stokes equations. These are kind of coarse-grained equations for the dynamics. And you'll notice that there are 6 terms in this partial differential equation. So the first thing I can do is I can compute at every point in space the first term of the equation, this u bar x. So this is literally a plot of that term of the equation in every point in space. And I can do that for all 6 terms in the equation. For every single term in this equation, I can compute these terms spatially. And you'll notice if you look at these pictures, you'll see immediately that there are different regions of space where 2 of the terms are active and the other ones are nearly 0. And there's other regions where other terms are active and other terms are nearly 0. And so this dominant balance appears to be holding in the data. And so what we're going to do, this is what Jared realized, is that every single point in space, there are 6 numbers that you can compute for each of these 6 terms in the equation. And so you can plot every spatial point in this 6-dimensional equation space. And so that's what we're plotting here. And these are 2-dimensional slices of our 6-dimensional equation space. Every white point is a spatial location from my full simulation. And so what Jared did essentially is apply rudimentary machine learning clustering, a Gaussian mixture model in this case, to find different regions in space. And then he applied subspace identification, sparse subspace identification. So each cluster, he tries to find the fewest coordinate directions that define the variance of that cluster. So you see that the red cluster is only governed by these 2 terms in the equation. The blue cluster is only governed by another 2 terms. And because all of these points are spatial, you can replot them in space. And we learn, in fact, that each of these clusters corresponds to a physical region of space where a different subset of the physics is active. So we're learning something fundamental about the physics of the situation just by using very, very simple machine learning techniques, clustering and subspace identification. And so we have applied this to lots of systems. So the boundary layer is the first one I showed you. We've applied this to the super continuum high energy laser to understand how nonlinearity propagates through this system. We've looked at the Gulf of Mexico, so geophysical flows, really complicated fluid flows in the ocean, to see where there are different regions where different local balances of weather might apply. And we're also applying this to neuroscience data to see if we can uncover patterns of the brain and of the nervous system to see if there are different ways that these balance laws hold. So this is something I'm really excited about. I think this is very new. This is kind of brand new out of our lab. And it's one of the areas I think has the most potential for new scientific discovery, applying this to disease models. I want to see what this looks like on the spread of COVID on a continent or the spread of malaria on a continent. I want to see what this looks like for a network of neurons in the visual cortex of an animal. These are really interesting things you can start to try for scientific discovery. Okay, so the next piece I'm going to tell you about is using these machine learning discovery techniques for reduced order modeling. So again, I love fluid flows, but in many, many situations, you have very complicated physics, but you want to get simple models, x dot equals f of x, that describe how these systems evolve in time. And so before I give you a bunch of examples in fluids, I want to give you my philosophy of the kinds of machine learning algorithms I want as a scientist and as an engineer. Because at the end of the day, I develop a lot of systems, control systems and models that are used in safety critical engineering applications. So I work a lot with Boeing, where we're developing technologies for wings and for engines. And if you're going to get on a plane that was designed with machine learning, you want that machine learning to be interpretable and generalizable. Same thing with self-driving cars, same thing with, in factories when you have humans and robots right next to each other. When the robots are using machine learning, you want those algorithms to be interpretable and generalizable. And we use neural networks a lot. I mean, I'm not trying to criticize neural networks. They're very powerful, but they struggle with interpretability and generalizability often. So what I mean by this kind of model, I think, is really nicely summarized by Newton's second law, F equals ma. This is a really good example of a model that's interpretable and generalizable. It's interpretable in the sense that it has very simple terms. It has three terms, F, M, and A. They have units. We can write them down for a particular problem and go to a coffee shop and analyze and discuss what these terms mean. It's generalizable in the sense that you can learn F equals ma from an apple falling on Earth, and it's still true when we land humans on the moon. This is the ultimate generalizability. Now, of course, you could train a neural network on videos of apples falling. You would need 1,000 videos of 1,000 apples falling, but you could train a neural network to do this. But that neural network will not be useful when we decide to land humans on Mars. Okay, so I'm not saying that we always need our models to have this kind of flexibility, but we would love for machine learning to be giving us models that are more like F equals ma and less like an opaque neural network. And so this has been a principle in physics from Aristotle to Einstein, this principle of parsimony, that the bits of a model that generalize. So I'm actually going to say that a very good working definition of physics are the pieces of a model that generalize. And to get physics, to get generalizable models, we want the models that are as simple as possible, but no simpler. And mathematically, that means we want to be promoting low dimensionality. We want models in terms of few variables, just like F equals ma. And we want sparse models. We want the fewest mechanisms that describe how those variables co-evolve as a differential equation. And we've come up with this schematic architecture for this kind of picture that illustrates what we want. So if we have high dimensional complex data X, I want to learn some embedding coordinate systems, some low dimensional coordinate system Z. This might be through some deep autoencoder. And I want to learn a differential equation in that Z variable, Z dot equals F of Z, that is simple and interpretable that we can discuss. Okay, good. So if we fast forward to the modern computational era, this looks a lot like the Lorenz 1963 model. So this model was designed to describe very complicated, chaotic thermal convection to describe weather patterns in the atmosphere. And you'll notice that this equation on the right has the same basic properties that we want our machine learning models to have. It's low dimensional in terms of three variables, X, Y, and Z. These are the amplitudes of spatial modes. And it's sparse. The right-hand side of this differential equation, out of all of the possible terms that could be used to describe these dynamics, this is a sparse system of 7 terms. 5 of them are linear. It's about the simplest model you could possibly write down for this observed physics. So that's what we want our machine learning algorithms to do. And so I'm going to tell you about our sparse identification of nonlinear dynamics algorithm that allows you to take data and learn dynamical systems. Systems of the form of ordinary or partial differential equations. So for example, if I have data from my Lorenz system, I want to learn a differential equation that's sparse and low dimensional. If I have data from a fluid flow, I might want to learn that the Navier-Stokes equations are the PDE that governs the system. And sometimes if I don't want a PDE, I might also write this as a low dimensional approximation, some expansion, and try to get an ordinary differential equation of that fluid flow. So I'm actually going to warm up and demonstrate this on the Lorenz system. So we're going to start with this as a warm-up problem. And let's pretend that we collect measurements from this system. We have data, but we have no idea what the equations are. So we measure X, Y, and Z, but we don't know the equations. So by far the simplest thing, if we measure X, Y, and Z and we compute their derivatives, is to build a linear model, a little 3x3 linear A matrix. This is what dynamic mode decomposition does, just a linear regression model. But we know that this is not going to be a good enough model because our original system is chaotic, it's rich, it's nonlinear. This is going to be an insufficient model to describe that dynamical system. And so what we do instead is we build an augmented right-hand side library that has more terms that could possibly describe the observed dynamics. This is kind of feature engineering, if you like. And so what we want to do now, now we have terms like x squared and xy and y squared that could describe our dynamics. And this library could include anything you like, sines and cosines, Bessel's functions, whatever you like, you can include here. I've just shown polynomials because it's simple. And so now we try to find the sparsest combination of these terms that add up to equal x dot, y dot, and z dot. And when we do this, we learn that the simplest model that describes the data has the exact same terms in the original differential equation. So purely from measurement data, we can learn a nonlinear differential equation that's most consistent with the data, that's sparse, that's interpretable. So that's the Cindy algorithm. And if you're interested in trying this, you can download the code. We have this on PyCindy. It's pretty well supported at this point, and there's a large community across the globe working on this. So the other kind of neat thing, this is work by Sam Rudy when he was a PhD student with us, is that you can also learn partial differential equations. So you can build a similar library, but now including partial derivatives in space and in time. And when you apply this algorithm, you can learn these partial differential equations like the Navier-Stokes equations. Now, of course, we already knew that this fluid flow was governed by the Navier-Stokes equations. That's knowledge we've already had. But since we wrote this original paper, our colleagues across the world have learned new systems that have never been written down before by humans, for plasma physics, for elastic systems, for systems where we didn't have governing equations. They're starting to learn new PDEs for those systems. So that really is discovery. Okay, good. So I'll give a couple more examples here. Maybe one of my favorite examples is learning reduced order models for fluids. So if I take the same system and instead of a partial differential equation, I want a reduced order ordinary differential equation model, I can essentially write this high dimensional system in a basis given by these three modes. And we learn that their dynamics are governed by this very, very simple differential equation in blue here. So even this very complex high dimensional fluid flow is governed by a relatively simple low order ordinary differential equation in blue. Again, just using the sparse regression procedure. And it's kind of fun. Jean-Christophe Loiseau, who's a close collaborator of mine, has shown that in the sparse regression algorithm, you can add in partial knowledge of the physics. So for example, we know that these fluid flows conserve energy through a skew symmetry in the quadratic terms. And so we can add these as equality constraints when we do our sparse regression, and by construction get models that conserve energy and are more stable. And when we do that, we find, so I'm going to show you how our models compare to the industry standard leading models on these two fluid flows. So what we have in the right column are the previous state-of-the-art models. This white curve is some quantity of interest, the ground truth drag measurement, a drag force. And the yellow and blue are the state-of-the-art models from before. They're kind of qualitatively okay, but quantitatively inaccurate. And when we allow ourselves to have these Cindy models that are constrained to be energy preserving, we almost perfectly quantitatively match these drag coefficients. And what's really nice about these Cindy models is that they're not just accurate, they're also simple, they're sparse. And so my friend JC was able to take this model, write it down on a napkin, go to a coffee shop, and manipulate it into this form here. This is the actual equation with the actual terms that generated that cylinder flow data. And so to date, this is the simplest and the most accurate model that describes this observed phenomenon. So that's pretty exciting. You get real interpretable, understandable dynamics because of the sparsity, because of the simplicity. You can also apply this to cases, this is a more complicated fluid flow, where we assume we actually can't measure the fluid. We can only measure the forces, the lift and drag on these three cylinders. So it turns out you can build these sparse nonlinear regression models directly on lift and drag forces, which is really cool also. Okay, so I'm going to take a step back. In all of the examples I showed you so far, we assumed we had access to the right measurements. So for example, in in the Lorenz equations, we assumed we knew that X, Y, and Z were the right measurements for the system. That's a huge assumption. In the fluid flow equations, we assumed that we knew these three modes, X, Y, and Z, were the right modes to measure our system in. But when we are interested in modeling new systems like the brain dynamics or a climate system, we might not know the right coordinates to measure in. And so I think it's really important to start thinking about how do we learn good coordinate systems and dynamics at the same time. And so deep autoencoder networks, neural network autoencoders, are a very powerful way of learning compact coordinate systems, good representations of your dynamics. And it turns out that you can learn dynamical systems in these autoencoder coordinate systems. So I want to give an analogy here because I think this is really exciting and interesting. Most of the physical breakthroughs in science and in physics and in engineering have occurred after the discovery of an appropriate coordinate system. So for example, let's think about our planetary view of the solar system. So this is how, at least in Western astronomy, we viewed our position in the universe for a really long time, for thousands of years. We are this blue dot, and when you look up at the night sky, you see the planets and our sun in this motion, these very, very complex orbits. Sometimes Mars turns around in its orbit. It doesn't always go in a circle, it turns around. And this is very, very hard to learn physics in this coordinate system. And so you need to change your coordinates to the heliocentric, where the sun is at the center, and everything becomes much simpler, and you can finally hope to learn elliptical orbits in F equals ma physics. So this is really important, okay? This idea that changing the coordinates is necessary to learn the dynamics sometimes. And so that motivated us to design this SINDI autoencoder optimization. So this is work by Kathleen Champion and Bethany Lush. Kathleen was a fantastic PhD student with Nathan Kutz and myself. Bethany was our postdoc. And here we are essentially combining the simple modeling of SINDI and this coordinate representation of the autoencoder. So we learn a coordinate system phi so that our dynamics Z can be sparse and nonlinear. It's a very stiff, difficult optimization. These are inherently coupled. You can't just learn an autoencoder and then learn a SINDI model. You have to learn them at the same time. It's very, very challenging. But in many cases, we've shown that this is possible to learn these coordinates and the dynamics at the same time. And so that's this picture here, but you can even go farther. You can constrain your dynamics not to just be sparse and nonlinear, but even linear. You can add an additional constraint. So what if I design an autoencoder that changes my coordinates to make my dynamics fully linear? This would be related to the Koopman operator theory. So actually a number of groups, maybe 6 or 7 groups across the world, have actually developed these Koopman autoencoders that learn coordinate transformations so that your systems behave or look linear. Very, very cool idea. And so we recently wrote a review paper on Koopman technology, and you can see kind of these coordinate transformations enable you to simplify your dynamical system. So we've applied this idea of SINDI and coordinate transformations to lots of systems. I'll just show you a couple of examples. So my fantastic PhD student, Alan Kaptanoglu, has essentially shown that you can model fusion reactor, spherical fusion reactor systems like magnetohydrodynamic systems using these simple models. So this is a 3D simulation of a spheramac fusion reactor. We have to learn a good coordinate system through some energy inner product, through some orthogonal inner product. And in that coordinate system, Alan showed that you can learn these sparse SINDI models that conserve energy, that are constrained to be physical, and they almost perfectly match the dynamics of the observed high-dimensional system. What's really neat about this is that the original high-fidelity simulations are far too expensive to run in real time with an experiment. But our simple SINDI models are very, very fast reduced order models that you can actually hope might run in parallel for model predictive control. So we're currently working with our experimental collaborators to try to build these into actual control campaigns for these devices. Now, instead of giving you a lot of other examples of applying this for fluid flows, maybe I'll show you that there are lots of examples. We've applied this to the fusion reactor, the cylinder flow, turbulent wake experiments behind wings and planes and trains and boats, electroconvective physics. And so maybe instead of going into all of these examples, I'll stop here and I'll take some questions. So just to summarize, in all of these cases, what we've tried to do is learn a simple differential equation, x dot equals f of x, in terms of a low dimensional feature x, the fewest variables needed to describe these complex systems, with the sparsest dynamical system f that we can get away with. And by promoting low dimensional and sparse dynamics, we hope that we find models that are as simple as possible, but no simpler, and learn the physics that generalizes in the system. Okay, so with that, I'm happy to take questions. And if you have any questions about these, I can kind of give you some of those examples. Thank you all for your attention.
Thank you, Steve. We finally met virtually in this Zoom meeting. I know you have a very busy schedule today. I hope you also enjoy the talks in this session as well.
Yeah, thank you.
So I have one question. I'm very interested in your Cindy methodology in getting system identification for highly nonlinear system like a turbulent flow, and you and I have both interest in turbulent flow. So, and you show some examples, getting predicting integral quantities of the like aerodynamics force. Is there any way you can expand this approach to not only the integral quantity, but also like some flow field data in the future in like a time series or more detailed flow field data in turbulent flow?
Yes, absolutely. So I'll show you a couple of examples of this actually. So there's a few really interesting examples of this. So the first thing that we've done is actually, here, let me pull up my slide here. So the first thing that we can do is apply this Cindy algorithm to learn, sorry, my screen is too small. We can essentially apply this Cindy algorithm to learn stochastic dynamical systems. So if I have a fully turbulent flow field, I might want to model the coherent structures in X as x dot equals f of x. But all of the multi-scale small scales that I'm truncating, I need to model those as correlated noise forcing, this sigma x WT. And so essentially we have modified our Cindy algorithm to learn stochastic differential equations. Kind of on the right, we can parameterize both the drift and the diffusion terms with Cindy. And we can run the same optimization to learn these representations. The figure I'm showing on the very right, this is from real turbulent wake experiments from George Regas at Imperial College, London, where these are very, very messy, noisy, turbulent experiments where we can learn these low dimensional models. So that's one example where this definitely works that we think is pretty exciting. One other example I'll show is, and this is not our work, this is our colleagues, Sarah Beetham and Jesse Caposalatro, have done some really cool work on applying this to closure modeling. So essentially they can learn these sparse RANS closure models using similar techniques, which we think is pretty exciting. And these are just a couple examples. There's lots of other examples where you can model, more subtle features of more turbulent flows. Yeah, great question. Thank you.
All right, thank you. Yeah. Well then, yeah, Professor Che, you can ask questions.
Thank you so much for the wonderful talk. I have some question. When we have, so our flow field has unexpected discontinuities over the time series. We often end up including many modes, and even though we are having fixed phenomena and stuff like that. So is your Cindy algorithm can handle those times as well?
Yeah, so if I understand the question, oftentimes our data has lots and lots of modes that are needed to describe this data. It's still hard to find a low dimensional representation. And we don't have a perfect answer for that. That's still a very challenging case when you have high dimensional, when it's hard to find a low dimensional representation. The Cindy autoencoder could help with that. We have not scaled this up to high dimensional fluids yet. So that's still an open problem of how to use these for fluids. I'll show you one example where we do this. We're getting close to that, is this moderate Reynolds number cavity. So this flow is still pretty simple, but we end up needing about 40 or 50 POD modes to describe the dynamics. And that's too many modes for our Cindy model. And so what we find actually is if we look at those 40 or 50 modes, what we can try to do is find a subset of 2 or 3 driving nonlinear oscillators that are dynamically the most relevant, that are causal, that cause all of the other 40 or 50 modes behavior. And then we only model those driving nonlinear oscillators. So for example, we do this using a nonlinear correlation analysis. This it's called the RDC, the randomized decorrelation coefficient. And essentially from this, each of these A1, A2, A3 are the amplitudes of our POD modes. So you can see that there's a lot of modes, but they have these correlated structures. And so through this analysis, we essentially learn that there are these 2 driving nonlinear oscillators in red and blue. And so we build a Cindy model for those 2, very, very simple Cindy model, just a Stewart-Landau with weak coupling. And then all of the other 40 modes are algebraically slaved to these A1, A5 modes. And by doing that, we get a very simple model, and we can predict all of the harmonics and all of the frequency crosstalk in this power spectrum. And we get very, very nice kind of rich dynamical systems. This is just one example that worked for us. That's still a very hard problem in general when you have really high dimensional representations. So a lot of open work to make that more robust and more universal. Thanks for the great question.
Oh, but I have one related question. So those are all the orthogonal bases, right? So is there any improvement if we include non-orthogonal bases into the representation?
Oh, absolutely, yeah. So I use orthogonal bases for fluid flows because they have nice properties and they're easy to compute. So for example, actually, this is work by J.C. Loiseau, my collaborator. He uses a non-orthogonal basis to build models for this problem. So he uses non-orthogonal bases quite often because this is a regression procedure. You can do this in non-orthogonal bases for sure.
I believe, in a system which includes, discontinuity, which requires many numbers of modes, if we include non-orthogonal bases a little bit, I thought we may be able to reduce the total number of modes.
That's a really good idea. Yeah, so the dynamic mode decomposition is trying to get these nearly parallel modes. It's trying to get modes that are for non-normal systems. And it's actually specifically designed for those kinds of turbulent systems that are very shear driven. And so I think that's a really good intuition. I haven't looked at that much, but I know Jean-Christophe Loiseau has a bit.
Okay, thanks a lot.
Yeah, thank you.